The talk is titled Science of AI and AI for Science. I'm not going to get into very much detail at all about AI for science, but that's sort of what we're driving towards, so I'll probably make a few comments about that as I go through. The first thing I want to do, though, before I get into my pitch for you about open models, I would like the world to understand the technology that we build better than they do now. It's become way more important than I ever expected. NLP used to be a really kind of niche topic that many departments in the world didn't even bother to think about hiring in. I felt lucky to even get a job when I graduated, and now it's like the complete opposite. Like everybody I talk to, whether they work in computer systems or computer science theory or whatever, they want to talk about language models, and that's great. But these things are also being put into the hands of everybody. Like your parents, your grandparents, right? So when ChatGPT came out, there were many things happened in my head, and one of the big ones was, oh no, we really need to be doing a better job of explaining this stuff to a wider audience. So with some of my students, I wrote a broad audience tutorial that's very non-technical. We got some help from a person who's really good at, who works for UW, who's really good at teasing apart writing so that it's accessible to a broad audience. We called it a guide for the perplexed. You get the joke? If you don't get the joke, read the guide. It will help you understand language models better than you do. Share it with your friends, your parents, anybody who has a stake in this technology. It came out on the first year anniversary of ChatGPT. I still think it's pretty timely and relevant. So it's just sitting there on the archive for anybody to use. I occasionally get email from someone working in medicine or something else, finance, saying, thanks for doing this. Please share it. I think it's a little contribution to making the world a little bit more aware and a little bit less mystified. The real point I want to focus on for most of the talk is the same position I took yesterday at the end of Shinji's nuts and bolts session. The reason we got here, the reason these models work so well, the reason our field has had so much success is that people used to talk openly about everything they did in the research community. And if you don't remember that, I'm sorry, you didn't live in the golden age. But it's only been in the past few years that technological advances, exciting technological advances in our field have been treated as trade secrets and proprietary. And I would like us to go back because despite what you hear from some of the tech companies, there's still a huge amount of work for us to do in academia and outside of the for-profit sector. These are just some of the things that motivate our team at AI2. I want to point specifically to work on efficiency, which we were talking about at dinner last night, should get more attention than it does. There's a huge amount of work still to be done on adapting these models for specific uses. I'm particularly excited about the use of language models in scientific advancement and as tools for scientists that tie together their literature and their data. We all do this every day, but we do it in a slow, inefficient, painful way. It's really hard to read all those papers. I think AI might be able to help us, but we should still be in control. Anyway, so there's still a lot to be done. And so our team had, after ChatGPT, we had kind of a long discussion internally. What should we be doing? How should we respond to these new developments where these language models are being widely used and claim to have incredible power, but they're not being studied scientifically because OpenAI didn't share very many details about how they built the model. And so we basically crafted this project to build fully open models for reproducibility, for transparency, to make it easier for more people to use and study the models themselves. And a friend of ours made this really nice analogy, inspirational analogy, I think, trying to do research, AI research on proprietary models. It's like trying to do astronomy based on pictures of the sky printed in the newspaper. Because the amount of information we get by just interacting with the model is nothing compared to what could be known. So our design principles in the Olmo project are to be fully open. That means we share everything, the code, the data, obviously the model weights, iterates of the models, checkpoints from along the training run, the recipes, the mixes, all the experimental details insofar as we can document them, so that you can understand and reproduce the work. At the end of the talk, I'll give a couple of examples of work done at UW by UW students that built on Olmo to just kind of highlight some cases where you can do new things because of the full openness. We also try to take a scientific approach. This is really hard when you are under constrained resources. I have a new appreciation for what goes into building a commercial language model. You have to make a lot of hard choices, and sometimes you're halfway through a run and you realize something was wrong. And taking the fully scientific approach of going back to the beginning and starting over and doing it right, which you would like to do, sometimes you can't afford to do. So we do the best we can. We document what we did so that others can learn and not have to repeat that effort and pay those costs again. And of course, we want the models to be high quality. And so I'm really proud that the Olmo models, when we release them, they have consistently matched competitive state-of-the-art models on benchmark performance. We also want them to be efficient. I'm not going to talk about that one so much today. I'm not going to go through the whole history of the whole chain of Olmo models. I think it's not the most interesting way to present the work. I think the papers really do them much better justice than I can do. But just here's the timeline. We've released about one model a year. The first Olmo was on par with Llama 2. That was back in late 2023, about 1 year into the project. And then we did Olmo 2 last year, and then we had like some extra cycles magically, and early this year we released a 32B model using the same recipe we had used earlier. So everything is matched except the size, and this model outperformed GPT 3.5 and 4.0 mini, which was just like huge for our team. It's like we're not catching up anymore. Open models are just as good. And here's the efficiency thing is we do this out of necessity. But the estimated total cost of training our models is generally better than similarly matched models that perform about as well. This is not across 0 benchmarks. That's a typo. It's 10 benchmarks. Before that got fixed for the camera-ready paper. So along with the models, we've released the pre-training data set, DOLMA. That was at ACL last year. We did a mixture of experts model called Olmo-E. We adapted that to run on your iPhone. So there's an iOS app that is open source. So if you want to build phone locally running on an iPhone, not my iPhone, it's a little too old, but a modern iPhone, language model applications, you can use Olmo-E and everything stays on the phone. Totally private. I'm not going to talk at all about the series of Tulu models, our recipes for post-training that were then applied to Olmo to make an instruct model. But that was groundbreaking work that showed that fully open resources could get you to a state-of-the-art model. Tulu 3, released late last year, was the first to introduce the idea of reinforcement learning with verifiable rewards. Our team's really proud of that. Others were doing it at the same time, absolutely, but we did publish it first. I'll talk a little bit about our new architecture, FlexOmo. I'll talk a little bit about our multimodal model, MOMO. I want to start with a few things that were kind of peripheral to the project, though, that we couldn't have done. That we would never have thought to do these things, and they ended up being just extremely exciting to various stakeholders. So I'll get to those in a minute. But overall, what we want is to empower you, the AI community, to inspect, reproduce, innovate, and move faster, and do things that right now, or up until very recently, only the really big labs could do. And I think we've argued very well that open models can do as well as closed models. You don't need to keep things secret to keep an edge. This was announced just a month ago. We received an award, an infrastructure grant from the National Science Foundation with matching support from NVIDIA. The project is called Open Multimodal AI Infrastructure to Accelerate Science. What the most important thing to say here is that we're going to keep building Olmos. That's what this is going to support for the next 5 years. What will be in those models, we don't know, because everything is changing so fast. I'm amazed that they gave us this much money without us saying exactly what was going to go in those models. We basically said, we're going to build 4 more models. Money, please. We said more than that. We argued, and I think this is really important, that generalist models were probably not going to be designed for use in the sciences. And if we wanted the full potential of this technology to support scientific research, not just in AI, but across scientific disciplines, linking data and literature and making things usable for a scientist who doesn't necessarily have AI expertise, then somebody had to do that, and it probably wasn't going to be the for-profit industry. So we sort of had both sides of the story. AI research needs open models. Scientific research that's going to use AI needs open models as well. So that's the quick story of that. My plan is to give you a few vignettes about recent developments in the Olmo ecosystem. It's a relatively non-technical talk. It's just a teaser so that you'll invite members of my team to come back and give you the details, or just go read the papers. I'll give a couple research highlights from work at UW that was enabled by Olmo, and then I'll talk about Blab just very quickly because there's many other co-authors on Blab in the room, and then hopefully lots of time for questions. Okay, so Olmo trace is a very simple idea. We think it's really hard to understand why models do what they do, and I'm not gonna argue that this gives you an explanation for why models do what they do. But one thing that we realized is that if you have access to the pre-training data and the post-training data and everything that was in the model's diet when it was constructed, when it was growing, then you can match back. You can do a fast match of the text that the model produced back to the data, and see in what context did the model see this. It's like when a kid says something cute. You're like, where did you hear that, right? So this tracing back, of course, it's a very large amount of data you have to trace back to, but we did it. You can use it. It's a feature called Olmo Trace in our the web interface to the Olmo models playground. So you ask a question about the Space Needle, and it generates some text. And if you opt into Olmo Trace, it'll highlight in green, and the green will be darker if there's more matches. And you can click the span. It's usually more than a few words. It's like an eerily long span of text that matches exactly. This is not information retrieval. This is exact string match. So we're using data structures and tools for bioinformatics here on trillions and trillions of words. And you can go back and see the context in which that string appeared in the data. You can see whether it was pre-training or post-training. You can see the larger document. You can see the URL. So this is, I don't know, really, it's really fast because our students are fantastic with algorithms. They're using a suffix array technique to search. After we published the initial paper using that suffix array, it was called Infinigrams. It was sort of a language modeling project initially. We got email from people in the bioinformatics world who were like, "Wait, there's a better algorithm," and so that led to yet another paper. So anyway, this is just it's like old things always come back. So I learned about suffix arrays way back in the days of phrase-based machine translation, I believe. A few people are smiling. Sometimes you learn something in grad school and it comes back and it's useful. This just made me so happy. But if you're using a language model and you want to understand why it's doing what it's doing, I think this is a first step. I don't think this gets us all the way there. I think we still need a lot more tools, and we produce many other tools. There's something called What's in My Big Data. There's a number of code bases that have come out of the project for inspecting and understanding the data, because we've invested quite a lot in cleaning up the data and in curating data. Speaking of which, when people build language models, they tend to rely pretty heavily on stuff that's already in a text, electronic text form, already digitized. And there's a lot of that on the web. But there's a lot of information, and particularly I think if you care about scientific use cases, there's a lot that's locked up in other kinds of documents, in PDFs, images of scans, God forbid, Google Docs, or Word, Microsoft Word. There's all these different formats, and converting them into training data is something that we felt could potentially unlock a lot of data, and it did. So after we did this project, we got about 1 trillion tokens, increasing our training data set by about 20%. For PDFs, and that will go into Olmo 3, which will be released later this year. I won't talk about Olmo 3 today. But of course, so we built the short version is we built an optical character recognition system. This is a problem that I know a lot of people care about, particularly in the digital humanities, because a huge amount of information never got digitized and never went onto the web. OCR it's a problem that, like, for some reason the NLP community and the speech community has anybody here ever worked on OCR? One person. Oh, 2. Okay. 1, 3. All right. I appreciate you. I don't know why this was such a fringe problem. Every now and then I would try to get a student to work on it, and nobody would ever get excited. They're like, "Can we even publish a paper about this? Nobody works on this." Anyway, so our engineers just did it. They used a language model. They fine-tuned a vision encoder for documents. They put a huge amount of work into the training data. They built an OCR system. It's open source. It's free. You can download it and use it. They also did they built a benchmark for it and compared it in accuracy to everything else they could find. And it's basically better. The cost per million pages is about $200, and that's just for running the hardware, right? So if you are willing, if you have a lot of data and you want to digitize it, this is probably the tool you want to use. And I happened to be at a meeting with digital humanities scholars and archivists, and they really were excited about this. This was a big thing. So I'm really proud that our team did this. So it's just sort of like a byproduct of like committing to we want to build this thing, we want to do it openly. This is a way to unlock the data, and a great research project pops out. So speaking of data, this is the part where I'm going to get a little bit more technical. So I think data is obviously incredibly important, and it's a huge. I guess you guys need a lot more petabytes than we do, but we have a lot more data than you do because text is so compressible. Mm-hmm. But anyway, it's not just about the volume of data. There's also issues around who really owns the data, what data are you allowed to use, what data are you willing to share. And I think one of the big obstacles to people really owning and adapting and customizing the technology for themselves is they need to be able to continue to own their data and use their data without necessarily sharing it. And so we were thinking about how to give more nuanced control in the language model construction process. This is a project that is under review. The core contributors are Wei Zhao, who's a PhD student, Akshita, who's an engineer on our team. Sewon is a former student. She's now faculty at Berkeley, who still works with AI2. The way we look at data when we do pre-training of a language model, you have to have it all right there when you do pre-training. Data is either in or out. If you're not allowed to use it, you just don't put it in the mix. And you have to make this decision at the beginning. If you realize you made a mistake later, or somebody says, hey, wait a minute, I'm the New York Times, you must not use my data, and you used it, you got to go back and start at the beginning. That's the kind of thing that gives a manager like me a heart attack because it's extremely expensive to go back and start at the beginning. The real world is that model developers may not have access to all the data for various reasons. Some data may be restricted in who can use it. You may want to be able to add data or remove it or opt out of using it later on. Data is not all the same. Data has different privileges. It has different value in different applications. There's a huge variety in, I hate the word quality, but I don't have a better word, right? Like some data is really good for some purposes and some data is really bad for some purposes and really unhelpful. I used to say nobody wants to use Reddit, and then I found out that like 90% of Reddit is incredibly high value stuff because it's people talking earnestly about really niche things. Some of it's garbage, but some of it's high value. So it really depends. I don't know who wants to train a language model on Disney, but the big idea in this project is to train different components on different data and then be able to mix and match at inference time. And so the tool that we use to get there is called a mixture of experts architecture. So on the left, you have your traditional kind of transformer block, as seen in the vast majority of models today. Mixture of experts models like our own open version, OLMO-E, they swap in something different for the feed-forward network, where at every token, the router decides a fixed size subset of modules to activate, and these are just copies of the feed-forward network. So you have to have a router that decides at each token who's going to be activated, and you have to have these sort of different experts. The way this is conventionally trained, those experts they're just sort of like parallel bits of neural net that learn different things, but nothing guides them to be different or to be differentiated other than what the model learns through end-to-end training and the data and gradient descent and all that. So you can't like look at an expert and be like, oh, this expert is really good at pronouns, or this expert's really good at Reddit or anything like. People try, but that's not what it's designed for. It's like everything else in neural net world. You try to interpret it at your peril. The idea here is to associate those different experts or groups of those different experts with different data. So you're going to train the experts locally without sharing the data. So the Washington Post expert only sees Washington Post data. It's trained by whoever owns that data. And at inference time, you can tell the router, hey, no Washington Post. Just opt out of that. Don't use those experts. And so you can change who has access to which parts of the model. The tricky part, the technical challenge, is how do you train the router to be domain aware so the experts work together without anybody ever having access to all the data, okay? If you have expertise in privacy, if you have expertise in, I don't know, there's a bunch of different fields of computer science where people think about these things. You're going to think of all kinds of clever solutions. Our solution, I think, is dead simple and probably could be improved. It basically says, first, we train the public model on public data that we all share. Then everybody makes a copy and trains their own MOE, which keeps a frozen copy of the public model and then essentially continues pre-training the other copy on their data. So it's like a branch. And so that purple Washington Post model builder is going to have, they're going to train a router that routes between the original public model and their model, and their new experts, the purple experts, and they're going to train those experts together in the router. So now what they have is an MOE that does either the public model or Washington Post. And similarly for the other participants in this, they're going to build their own experts. And then at the end, we put it all together. And the router that has learned to distinguish or to decide between the public model and each individual expert magically is able to decide among all the experts together. That's the basic idea. So we did a bunch of experiments. I don't want to spend a lot of time talking about this, but we simulated a whole bunch of different mixes of data for the different experts, thinking about cases where there might be data that couldn't be shared or that people wouldn't want to share. We evaluated across 30 different benchmarks. The short version, somebody said something about boring numbers yesterday. It's just, you can read the paper for all the details. I'm going to give you a quick scan. FlexOlmo, over there, second from the right, beats all the prior model merging methods. It also beats individual experts on the specific domains. Even when we drill down into domain-specific evaluations, so these are math evals, the math expert is the best thing at math, except for FlexOlmo, which is a little bit better. At the far right, you have an MOE that just had access to all the data, so you don't get any of the modularity, and it doesn't even work as well. You actually are getting some benefit from separating out the data and specializing the experts. There's a lot more to say about this. The paper is on archive. I think this is a really exciting approach. I'm hoping that it becomes the basis for a whole lot more work where we can kind of asynchronously develop components to the model instead of building one big monolithic thing that all needs all the data at the beginning. Aside from the data sharing and privacy things, I'm really hoping this is a great way to do branches to add new modalities, right? So you build your model, and then you train like the speech experts, and then you mix them back in later, and now your model can do speech, and you didn't have to update everything. Maybe. I don't know if it'll work. Let me know if you try it and it works, let me know. If you tried it and it didn't work, let me know. I want to briefly talk about MOMO. This was our foray into multimodal. I should mention there's a new ASR model, a fully open ASR model called OMO ASR that came out from AI2 last week. We're very excited about it. Please don't ask me questions about it. I didn't help. All I did to help was say, okay, yes, please work on this to members of my team who wanted to work on it. It sounds great. I'm really excited to learn more about it, but I'm not the person to answer questions. You should reach out to that team and check out the paper. But I was involved in MOMO. And so this was our foray into late fusion vision language models. It's probably pretty familiar to you. Instead of audio tokens going in, you're going to have visual tokens that are constructed by looking at pieces of the input image. So this is a model that only takes images as input. It does not generate images, but it does generate sort of like little commands, like point to this particular point. These particular coordinates in the picture. So you can say point to Mount Rainier, and MOMO will find it in the image if it's a clear day. And you can see Rainier, which happens about half the time in Seattle. Boring numbers on both academic benchmarks and human preference ELO ratings. We did an extensive human evaluation. It really strongly beat pretty much all the other open weight models. It also was on par with the very best API-only models. So here we are, like basically the same human preference score as GPT-4o and ahead of everything else. Also, it came out the same day as Llama 3.2 by coincidence, and it was better and more open. Okay, but there's more. The amazing thing, and this is where there's a recurring theme, I think, in everything that's coming out of our group, including, by the way, OMO ASR. As I understand it, a big part of that story was curation of very high quality data. I think like if you want to summarize how do we build these awesome models, we spend a lot of time on really, really good data. So here, this is the part of the story that I think is kind of the most interesting and memorable. If you look at what Llama 3.1v trained their model on, at the end of the day, when you do late fusion, you have to have something that links images and text. Just like in speech, if you're going to do one of these speech language models, you have to have some transcribed speech to tie together the word tokens and the sound tokens, right? How do we do it? Well, we need data, and so these are basically like images with captions, and they trained on 6 billion of these. Our data set for this Pixmo is only 700,000 image text pairs, also fully open, right? Why is it so much better with so much less data, with orders of magnitude less data? If you go and actually look at the image text data that people build these models on, it's incredibly unsatisfying. It's like a few words about the image, right? That's a really interesting image, and all you get is pink Japan aesthetic image. Like the last word is even redundant. Obviously, it's an image, right? And this, like, love this picture. This is from de-identification, right? We take people's names out. Love this picture by person. This winter picture. Oh, great. So it says the only thing there is winter, and somebody's feelings. So this is the kind of data that's in Pixmo. You have a lot of pictures that are it's open domain stuff that you can download, and we have the license to use. Often very mundane, kind of boring pictures, but very rich, dense descriptions from people. People, it's funny, people are happy to tell you what's in a picture if you pay them enough money. Even a really boring picture, like somebody's tablet, like, look at that, isn't that crazy? Somebody can talk about the Gmail app icon and the M and like that. So here was the trick, and I think this audience is going to especially love it. If you ask people to do this, and you give them a text box, they hate you. If you ask people to do this and you ask them to just talk into a microphone, they can do it all day long. They are happy to talk for 60 to 90 seconds about an image, and it turns out, thanks to you, much appreciation, speech recognition is very good, and so we can convert this audio description of the image into text, and we're good to go. That's how we did it. So thank you. Sorry.
This means that you can also have a speech data corresponding to this?
Do we have the speech data?
And can we deduce it there? It is very variable, right?
Deeply appreciate your question, and I'm not sure because I don't know what we may have promised the annotators that we would not use their voices.
Yeah, consent form is required.
We may not have had that in the consent form, but I will forget about this in 3 minutes. But if you email me, I will find out.
Okay.
Yeah, it's a fantastic question.
Consider next time to include.
Yeah, next round.
Consider next time to include.
Next time we do it, if we do
this.
this again. Yeah. Great point. Okay, so and there's a
just as you mentioned, like since that you mentioned, you transcribe, let them speak and transcribe, and you're talking about the context about high quality data matters.
Yeah.
So I'm wondering if there's some kind of approach that you made that the word error rates or the ASR systems made in the process of transcription. Somehow you dealt with
we didn't do anything special. I think we did qualitative checking that the ASR was reasonably good, and consistently it was. The other trick, this is no secret, is pay people for their work, and they do better work. We invested a lot of money in that because we thought it was worth it, right? We thought having a high quality, but yeah, there's probably some speech errors, and honestly, that may be okay, right? Like I think there's a certain amount of recovery that happens just by having enough data. So there's a ton of stuff in Pixmo, all kinds of instruction following. The pointing thing I think was kind of new. So teaching the model, it's kind of bold to call it action, but a model that can just point at the picture and say, where's the menu, where's this or that. This turns out to be, people really loved it and used it, and it's become very commonplace. It can count. You can say, where are the boats? Count the boats. And it puts a little pink dot. I tried it the other day. I had a picture of some like cute monkeys, and I asked our model to count the monkey ears, and the internal version basically told me that this was not safe for work, and I wasn't allowed to ask for that. And then, but the published version of Momo was happy to count, and it correctly counted the ears on the monkeys. It was really cute. It can find the text in the image and essentially do character recognition and tell you what the text says. lots of pointing. If you ask it, it's interesting, we trained it to count things up to like 40. I think after 40 it can't count anymore. It's more open than anything else. I have to point to the one way in which the most open version of Momo is not perfectly open. So we have that's two versions that are built on our own models. So Momo 7BO is built on Momo, Momo 1BE is built on our mixture of experts. The one thing that's not open, the vision encoder here was CLIP. So as great as CLIP is, there was no fully open competitor to CLIP at that time that we wanted to use. So that's the data and the code for the vision encoder aren't out. I believe the new Momo coming out later this year or soon will be 100% open. Okay, so this ecosystem continues to grow, and I think I'm extremely hopeful for the potential for these models to enable research in academia, maybe improve public AI literacy. I don't have brilliant ideas about how to do that apart from our little contribution of the tutorial. But every time I see somebody say, oh, we wanted to fine-tune the models, so we used Llama or Quen or something like that, it's like a tiny little dagger in my heart. Use Olmo. It's fully open. You can see the data. You'll be contributing back to this growing ecosystem of tools for science. Lots of people are doing it. There's a huge amount of work on studying pre-training, informing policy, understanding what's going on, new architectures, studying forgetting. Lots and lots of people. This is months old. There's a huge number of new lines of work that are using Olmo, and I'm gonna next talk about a few of them. I still have 20 minutes, maybe 30. Oh, good. I don't have to rush. There will be plenty of time for questions, I think. So I wear one hat as a director of this project at AI2, and then I'm also still a professor at UW, where I have PhD students, many of whom don't work on Olmo exactly, or at all. I have people working on lots of different things. Some of them are not even language. Some of them are now working on music. But I wanted to point to a couple of examples where students at UW, and I'm mentioning UW projects because I know them well and I was involved in them. I think there are lots of other examples, but just kind of like things they couldn't have done if we didn't have Olmo. So the first one, I was really delighted to see all these talks about tokenization yesterday. I think tokenization is a fascinating problem that's a thorn in our side. This is going to be kind of a different take, but this is a tokenization problem. We call it super BPE. So people know BPE? Okay, good. So biparent coding method is kind of the starting point for building most tokenizers for text language models today. So this space travel thing is a bit of a pun. It's about white space. So I don't know how well you know BPE. I did not know this, even though I'd been teaching it for some time, until we delved into this project. When you do BPE, the first thing you do is something called pre-tokenization, which sets up some hard rules. You are never going to merge two vocabulary items across white space. So it really only can learn what we call subwords. That's not totally true because in Chinese there's no white space, so it's going to behave pretty differently for Chinese. But let's talk about English for a minute. You are never going to merge things that are multi-word expressions. You are never going to, So this example at the bottom actually shows how one version of Super BPE tokenizes the text. So this is BPE. It's basically word level. The white spaces are kind of tacked on. The punctuation is split off. This reminds me a lot of old school NLP tokenizers. Super BPE is enabled to merge across white space. That's really the whole thing. I will point out there's a lot of interest in the NLP community now around kind of byte level models or models that treat the text in a different way where there aren't hard token boundaries or where you learn patches or things like that. That's all very interesting, but we're going in the opposite direction. Here we're thinking about bigger tokens. We call them super words, okay, because they're bigger than words. Why would you do this? Well, one of the original motivations for this was encoding efficiency. So if you look at these two sequences, it's the same text. It's 40 bytes of text in UTF-8 or whatever. The first one has 13 tokens, so you're packing 5.7 bytes into each token. The second one, the second one has 7 tokens. Did I do this wrong? Did I get the numbers backwards? I did. I'm glad I caught that. Basically, you're getting better compression here because you're packing the same number of bytes into fewer tokens. Don't look at the decimal numbers, just look at the fractions. Everybody knows 40 over 7 is bigger than 40 over 7. Need to fix that. So this is the idea. It's very, very simple. When you do BPE, it's a greedy algorithm that iteratively merges vocabulary items to build your vocabulary until you get to the target vocabulary size. So let's assume we have a target vocabulary size of 200,000, pretty typical. If you do BPE and you track the bytes per token as you're doing the merges, you get this blue curve. After about 40K, 60K, you're getting diminishing returns each time you do a merge. You're getting more and more big tokens, but they're not used very commonly. They're rare. When you do super BPE, you make one change. You pick a time step in the sequence of merges, somewhere between 0 and 200,000, and you say, all right, relax the pre-tokenization constraint. Now you are allowed to start merging across white space. You could do that at the beginning and just say, don't do pre-tokenization. You can always merge across white space. That will give you the green curve, which will give you much better efficiency. Unfortunately, it gives you some really weird tokens. It tends to break words. It'll like merge the first part of one word and the second part of another. It's ugly. It doesn't work very well. So what we do is we have a curriculum. We start by doing BPE, and then at some point, maybe 20,000, maybe 100,000, maybe 140,000, we say, all right, now you're allowed to merge across words. And what you see are those kind of those branching offs from the blue curve are what happens when you change the curriculum and now allow merging across white space. You get much better encoding efficiency. Unfortunately, you can't write a paper about encoding efficiency. You have to go and do experiments with a real model and see what actually happens. So where are we going to find a model where we can completely reproduce the training and only change the tokenization and see if we get exactly the same result? You need OLMO. So I'm going to summarize a whole lot of experiments with one plot. OLMO with BPE, this is a 7B model, is the blue line, and this is tracking performance across 30 different, very diverse tasks. So higher is better. As you pay training flops, you get mostly better over time. And then you can say, all right, well, if I'm using super BPE, if I keep the model the same size and fix the same training compute, what happens is I get to train on more text. Because I'm packing in more tokens, more text into the same number of tokens. The tokens are bigger. So I effectively get to train on more data for the same cost. Also, by the way, inference is cheaper because every time I make a prediction at inference time, I'm getting on average more tokens. Right? So I'm getting like a 35% improvement in inference costs and a 41% more text. So is that fair? If you think that's a fair comparison, then look at the purple curve. And that shows you when we change 20,000 steps before the end of BPE, we switch, we allow merging across white space. Now we get a different vocabulary, and we keep everything else the same. We now get to train on more data, and you can see the difference between the dark purple curve and the blue curve. Much better performance. Another option is to say, well, that's not fair. It got more data. So let's keep the same amount of data. But if I keep the same amount of data with the same compute, I could actually have a bigger model. I could get more parameters. So let's use an 11B model. So now the compute is matched, the data is matched, the inference compute is about the same, the model's bigger. I don't know if that's good or bad. Personally, I'm agnostic. That also gets a win. So either way, that's the green curve. Either way, you're outperforming what you would have gotten with BPE. So choose the way you want to win. You have options. You had a question.
Yeah, does it also reduce the vocabulary size and also part of the parameters?
No, we fixed the vocabulary size at 20K.
Okay.
I'm sorry, 200K. You could do that, and we didn't do those experiments. So you could say, all right, I'm going to have half the vocabulary, but I'm going to do more aggressive merging. That might be a win. Yeah.
Can super BPE merge across any punctuation,
Yes,
including periods, exclamation point?
I think so. I think it's basically no pre-tokenization, but there's like a 20% chance I'm wrong, and it may just be the white space.
So we can't compare perplexity.
No, No.
I was just thinking, if at least it was forced to split at sentence boundaries, we
You
could
could do-
consider sentence perplexity.
So yeah, so the thing people do, and I still am nervous about this when they have different vocabularies, is they use this bits per byte conversion, which has there's a reason to not, but like it's probably okay. I don't remember if we put bits per byte. I think we had that in the paper, and I think it's about the same, maybe a little better. That's what I remember.
What's happening with multilingual case?
That is work in progress, and I don't know yet, but we're working on it. Yeah. My belief is that it makes no difference for Chinese because Chinese didn't have the white space anyway, but for other languages, I think we're seeing similar gains. But the evals there, I don't trust as much.
The
Right?
question is what's happening, for example, Latin group of languages. You share a lot of similarities, so that means your vocabulary will be repeating across the
Yep,
languages.
that's right.
So that means you can share more in multilingual space in
Yeah.
terms of representation.
Although there's a possibility that when you start doing cross white space merges, that hurts you multilingually because different languages will have different contexts in which they use the same
Yeah,
word.
true. That's why I'm asking in terms of,
Great question. We
can
don't
we
know yet.
share better multilinguality between languages?
Yeah, so by the way, I will apologize that Olmo is English only. I mean, no language model is English only because there's no perfect language ID. So Olmo actually does have some multilingual capabilities despite our attempts to filter out non-English. The reason it is English only is because we are a small team. We wanted to make sure the data was very high quality. We wanted to get a proof of concept. I hold out hope that a future Olmo will be multilingual. But with this push towards scientific use cases, if we have to choose, it might stay English for a while because that's where most of the science is. That's not my fault. I'm sorry. I wish it wasn't so. I did fight for Olmo to be multilingual at the beginning, and I lost. Okay. Any other questions about Super BPE? I know this is like a really brief, high-level, unsatisfactory summary, but I just want you to go read the paper. Yeah.
Just a small thing. So is BP down on the byte level or you stop at the character level?
Bytes. I'm pretty sure bytes.
Okay.
I'm
So
pretty
all
sure
the
bytes.
emojis and everything can be
All in there.
Okay.
Yeah.
Does this impact the self-introspection capability of the model? So like, does this suffer from more of the strawberry 3R problem where now you've merged across tokens and you have an inability to look into the tokens themselves?
There is a weird corner case where like if the prompt boundary is like in the middle of a token and it has to tokenize thing in a weird way, it can then have a strange effect on what follows. And we have like some technical work following on to try and fix that. But I believe like string manipulation, like the strawberry thing, is included in these benchmarks, and I think it did not hurt. Yeah, but there is a potential issue where like if your prompt ends mid token, and so it uses a weird token for this like, orphan part of a token that should be a full token, then the distribution that follows might be a little wonky. And we think we have a fix for that. But. Okay. So this is a totally new project you haven't seen because it's not out. It's just under review. It hasn't been published. One of the things I've been really curious, so I think I said this yesterday, everything that happens in models is because of the data, right? So my motto is it's the data, stupid. There is no emergence. Models do not have intelligence. They're just really good at doing things that look like what they saw in the training data. And the interesting question is, what does it mean to look like what it saw in the training data? So this project delves into that a little bit. Rahul's a senior PhD student in my group, and we were talking for a long time about how we could study, how could we do really fine-grained studies on how models behave as a function of their training data. So I'm going to give you a really high-level view of this project. We looked at a few different benchmarks, and we looked at the Olmo checkpoints over time and asked how many instances are learned between each pair of checkpoints. So what does it mean to be learned? It means at every time step before this checkpoint, where performance could be measured, the model got it wrong. And at every time step after, the model got it right. So we're only looking at a subset of instances from the benchmarks here. Because a lot of things never get learned. A lot of things get learned and then forgotten and then learned again. A lot of things get learned very early and they were never hard. But at each time step, we can find some set, sometimes more than 1,000 things, from a benchmark that were learned at that moment and never forgotten after. And we think that's kind of interesting. And the question is, what happened during that time step, during that one, I guess it's usually like 1,000 or a few hundred steps of training from one checkpoint to the next that caused the model to learn this thing. And if you really want to study causation, you really need to do interventions. You need to go into the pre-training data and change what the model saw from between those two time steps and rerun the training. So basically this paper is proposing a methodology for doing that. You look at your benchmark, you see what items were learned, you go back to the batch of data that the model saw during that learning increment, and you find documents that match. That is non-trivial. For some benchmarks, this is really easy. For others, this is a really interesting research question. What does it mean for a document to match one of these questions? You go back to the training data, and then you interfere. So you replace those documents. For example, if you want to suppress learning, or you want to see if you can prevent the model from learning what the capital of Paris is, that should say the capital of France. I hate when I catch these things in the talk. It's always in the talk that I catch them. It's never when we're working on the paper. I should say the capital of France. Where was Einstein born? So if you can match those questions to documents, and you want to see if you can suppress learning those facts, then the idea would be to replace the documents in the pre-training batch with same-size documents that don't mention the same information, and see if you can prevent learning. And the summary is that you can do it. So a couple interesting points. On the left, we have a graph where we were trying to suppress learning. So these are two different points during learning, two different checkpoints at which a bunch of instances had been learned. So we're looking at the populations of things that were learned precisely between this step and the prior one. So they had 100%. That batch had 100% accuracy on the original OMO run at this point. When we retrain on exactly the same data, with exactly the same settings, using the optimizer state and everything else, you get the blue bar. It turns out that everything is totally unstable. You can never perfectly reproduce one checkpoint to the next, because GPUs. Sorry, okay. So blue is that's what it means to have learned. Most of the time, most of these things did get learned again from the same data on a repeat. This is a benchmark where it's very easy to find matches because it's about very straightforward relations between entities in the world. It's called parallel. It's not a very flashy benchmark, but it's perfect for this study. So we go back to the pre-training data. Paris, France is one of the items that you're supposed to learn. It's a relation. You go back, you find any time Paris and France co-occurred in the same document. You replace that document, and you're able to push down learning by a significant amount, but it doesn't prevent learning all the time. So interestingly, there's stuff going on prior to this, or there's other things in this batch of data that are allowing learning to still happen sometimes. So we can make a dent. We believe that there is an effect. Obviously, if you remove every instance of Paris or France, just an occurrence of either term, you have that interestingly has a much stronger effect on learning, and we get below chance. We also did experiments to try and promote learning, where we took things that were not learned at this time step but would be learned later, and we introduced documents that show the co-occurrences, and we're able to boost learning by a lot, but not to 100%. There's a lot more in the paper. Lots of other benchmarks were explored here, and we found similar effects across it's mostly about factual knowledge. So I think there's a lot of capabilities that could be studied with similar interventions. But to be honest, I think a huge amount of magic has to go into how you match the documents. And one of the takeaways for me was that tools for doing retrieval, like information retrieval inspired techniques for matching a test item to documents, there's a lot more work to be done there to make this work better. We tried DPO, we tried classic things like BM25. There's a question over here.
Yeah. Do these experiments still preserve performance on items outside of the things you remove? Because it's possible that removing occurrences hurts the entire model in general.
Yeah, I cannot remember if we looked at that. I'm pretty sure we didn't put it in the paper. I think we did measure it to see, like we had control groups to make sure that this wasn't affecting other things we weren't intervening on. And I think it all checked out okay, but we didn't say much about it in the paper. So I'm now anticipating that a smart reviewer will ask the same question. It's a good question. Yeah. Okay, I have one more thing I want to mention, which is completely different. My student Oreva is very, very interested in big picture stuff in expanding the set of languages and dialects that can be served by today's technology. And I think partly because my training was around speech people a lot of the time, I was very open to this realization early in her PhD that if you want to study dialects, then you have to deal with speech. This stuff doesn't get reflected very well in text. I'm preaching to the choir here, but as an NLP person, this is humbling, and we quickly realized that it was very, very hard to do NLP research on dialects if you weren't basically thinking about speech. So we started thinking a lot about speech, and Oreva was kind of following what was going on in speech language models, and I don't know, we kind of had this realization that the models that supposedly, the frontier models, the published models, the ones that are being put out by the big companies that supposedly do things with audio, they're quite limited in the kinds of audio they can work with. And the most striking thing was that they can't deal with pieces of audio that are longer than 30 seconds. And we know why, it's great that these things exist, but we can think of so many things that would be useful to do if you could deal with arbitrarily long audio. So we brainstormed those, and with a bunch of collaborators, some of whom are in the room and can probably tell you much more than I can about some of these tasks, we put together something called the Brutally Long Audio Bench Lab, which includes things like, here's a podcast. How many people spoke in this podcast? And it's like an hour long, right? So the average item in Blab is 51 minutes. I said brutal, and I meant really long, right? So this is kind of one of the ways that I think if you want to get into an area that's a little different from what you're used to, and I've had the same experience with other modalities like visual processing, start by thinking about the evals, because as an outsider, you're going to have a lot of stupid questions that have very awkward answers from people in the community. And so I'm not saying that my team is going to start working heavily on audio or speech, but it is really interesting to dive in and say where do the evaluations in this area not make sense yet, or where could they be improved? So anyway, I hope this is useful, and you should ask Shinji or Martin, or do we have other co-authors in the room? There were a bunch of people in this paper. Yeah. Okay. These are the people to ask questions of. I'm just the advisor. Okay, so my parting thoughts. AI serves people better when it's open. If you are working in academia, you are benefiting from huge amounts of work that was done openly for many, many generations going back way before me. And it's a scary world if we don't continue to have that. Open models are not second rate. They are competitive. You are not sacrificing on quality by choosing an open model, and you are contributing back to making it better when you choose a fully open model. I hope that openness will accelerate science, both in AI and outside, by giving tools to people for whom the tech companies have no interest in building. So join us. Use the models, improve them, make your own open models, share them with us, tell us about them, and hire our people, because a bunch of them are graduating really soon. So I will stop there. I will put their pictures up and take whatever questions you have.
We have 6 minutes for questions.
That should be enough for Karen.
So you mentioned efficiency, and we talked about it yesterday as well. I assume some of the efficiency comes from better data curation, so you get more out of less data. Can you say more about any other sources of efficiency?
Yes, I can say a little bit. So one of the there's a slide that's often in the deck that I didn't share here about between OLMO 1 and OLMO 2. We learned a lot. And our engineers basically focused really heavily on improving throughput. And it's the kind of stuff that's going to make most of the people in this room, our eyes are going to glaze. My eyes glaze over. I don't understand this stuff, right? I've never programmed for GPUs. I've never done distributed computing across GPU clusters. But there's a huge amount of work that you need to do if you want to make the best use of that cluster to train your model. Because you've got a lot of GPUs working in parallel, right? And so it's the classic thing about communication, and you need really good interconnect. Actually, it turned out, so this is not being recorded, right?
It is, but
Okay, well, I'll just say the first cluster we built on. I mentioned Lumi yesterday, right? We didn't get great. Like there were a lot of challenges with using that hardware. PyTorch had not been adapted for AMD hardware, but once we switched to more conventional GPU settings, there was a lot more kind of infrastructure and knowledge about how to make things more efficient. But then once our team had developed the experience of working with it, they were able to go into our code base and improve the throughput tremendously. So I'm terrible at remembering numbers, but the improvement in throughput was just huge. So like each model we built, we've been able to train much, much more efficiently and faster. Now, does that mean that we burn less carbon? Not exactly. What it usually means is we can do more experiments to do a better job of choosing the data mix, of deciding on the learning rate, hyperparameter kind of stuff. So, I don't want to claim like the moral high ground, but it's like, well, it's definitely better if we can make things more efficient. In the long run, I'm hoping we like understand this stuff so we can like make a calculation at the front and know what to do and not have to run a million experiments to figure out how to set the learning rate. Learning rate, hyperparameter kinds of things, just maddening how many choices there are and how little scientific knowledge there is about it.
Sorry, just a quick follow-up. Can I go back to the first part of my question? So I assume that some of the efficiency came from data curation.
I
Is
think
that
so.
true?
I mean,
can that be quantified?
That we, in theory, you could do an experiment where you take a version of our data that's less carefully curated, like roll back the process and pick an earlier point and see what would have been different. We haven't done that. That would be a pretty expensive experiment.
So in the end, you ended up using similar amounts of data.
Well,
to
no,
other
actually,
models,
I think
is that a comparison we can make?
Yeah, you can always like train models with different amounts of. I mean, we effectively do that because we see the curve, right? We see things getting better. I think that the amount of data we're using is less than some of the other models, but it's not 100% apples to apples, right? We don't know what data they used, but also the data interacts with the learning rate schedule, and so you kind of like there is. Correct me if you know more than I do about this, but there's no way to say at the beginning, I'm going to start learning and I'll stop when I feel like it. You have to kind of know exactly how much data you're going to train on so that you can set the learning rate schedule to plan for when the plane is going to land. And we tried some things that might have given us, there's something called WSD, which is a warm-up, I want to say warm-up cruise decay, but that's not WSD. It's like warm-up something. Anyway, you can kind of keep the learning rate where you want for a long time and decide later when you're going to stop. It did not work for us. So basically, we don't live in a world where we can kind of do really clean experiments and believe the results well. But I would like to think that by curating better data, we are wasting less time training on stuff we don't need. I would like to think that. Yeah.
Can I do a follow-up question? So we had like a huge amount of interest and importance, emphasis in the data quality. I was thinking is there some kind of threshold bar that you set? So the two examples you showed, that's like quite easy to tell one's like not of good quality, one is a very good quality. But when you're doing like you're getting human annotators, you're doing ASR, you get all these different sets of data. So I wonder how you set the bar to include the data because there's obviously going to be a trade-off, right?
Yeah. So I think it's even worse than that because we don't have quantitative metrics for quality.
Mm-hmm. Exactly.
Right. So it's more like we have components of the data mix that are targeting a particular thing. Like this is meant to be really useful for as representative of scientific papers. This is meant to be represent Reddit. This is meant it's sort of like in the FlexOmo setting, right? Like there are different components to the data, and a huge amount of work goes into trying to make it high quality from the perspective of what you think high quality means in that domain.
The domain dependent
within the domain, and then you do experimentation to decide how you're going to mix those, like what rate, what fraction of the data should be web versus PDFs from science versus this.
Basically, there was some kind of ablations on the
huge amount of ablation experiments with smaller models to decide on the mix. But in terms of like the data quality, it's an iterative process. You've got people looking at samples of the data all the time. It's a kind of subjective thing. I kind of think of it as something that could go on forever. Ideally, yes, we would have quantitative ways to talk about quality, but I actually think it's like a politically loaded thing to say that this. We had a paper a few years ago. People may have seen it, basically arguing that you are taking a political position when you say that some data is higher quality than others. And when, like, we looked at the GPT-3 quality filter, which we could reproduce because it was open, and we found that when you applied that, it was basically saying, is it more like news in Wikipedia or random web? And what we found was that it was strongly biased against language from people who don't speak a standard dialect, against people who are young, against people who, you know, and anything more casual. It was really biased against like Nobel Prize winning poets. It doesn't like art, right? It likes plain spoken newspeak. So you know, what does quality mean? Whose data counts as high quality was the title of the paper. I think this is a very tricky question. You can't get away from it. There's a lot of stuff you absolutely don't want to train your model on. I'm not saying quality isn't a real thing, but it is very, I think, very contingent. This is one of the reasons, again, I think it's important to think about what is the end use of the model? What is it for? Is it going to be in front of children? Is it just going to be in front of scientists? Because I think scientists can handle profanity, right? But there's other stuff scientists absolutely don't want in their pre-training data.
Let's take one more question.
Yeah, you mentioned that there is no emergent capability. Now, my question
I
is...
knew that was a hot take that would break the
Great. I'm wondering, do you find anything surprising or very exciting?
Oh, I have an anecdote that you will love. Okay, so I didn't talk. We seem to be moved. We have moved out of the world now where we get these like heart-stopping spikes in the training loss. You know, you're doing a run that's going to last weeks, and somewhere the training. So one morning, an engineer goes in and checks on how things are going and looks at the weights and biases log, and the training has spiked. The loss has spiked, and you're like, shit. Is the whole thing done? Like, this has happened. We have started runs, and the spikes got so bad we had to kill. Okay, so there was a point, I don't remember, it was somewhere in the OMO 1 time, people did a deep dive on this crazy spike. Like, what's going on? It's probably in the data. We're looking at a lot of things, and they're looking at the data, and they traced it down to a very, very specific thing on Reddit. So, I will be shocked if anybody has heard of this, but there is a Reddit called the Microwave Gang. You've heard the talk before.
Yeah.
No, I saw the paper.
It's in the paper. Okay, well I'll give, okay. So, the Microwave Gang is a Reddit for people who, they go and they post, and every post has essentially the same form. Beep. That's just what people post, because the internet is weird and people do weird stuff on the internet, and we didn't filter this out. Okay, so this was in there, the motto was like, this is surprising, I wasn't expecting another M, and another M, and another M, so it spiked, and so, you know, that always gives like heart attacks to the engineering team. And so we started filtering things that have long repetitions of the same engram over and over. And so that was one little lesson that was learned. Was that Reddit low quality?
Good question.
I don't know. Like somewhere there's a kid who like wants to play the Microwave Gang game with a chatbot, with our chatbot, and it's not going to work. I don't know.
Thank you.
Yeah.
So, I want to ask a follow-up question. So can you add a tab or something to situate the model to deal with data from different domains? So that when you train the model knows it's from Reddit. So
Yeah. This idea has been batted around where you give. I was thinking of it in even a more rich way, like a prefix before every document. You like have some generated text that's like the next thing you're about to read is a web page from 1994, and you know like it came from this domain, blah blah blah, and it's just like some language situating it and putting it in context. I think that I don't know if people do that. I don't think we do it. I think something like that would be really, really cool.
Yeah, I remember seeing some Google's generation. They always have this tab, bracket.
Yeah.
Some other thing. Right?
Yeah.
But maybe you can make that look.
I don't think we do that, but yeah, I think it could be. I think something like that would be really good, and maybe we are doing it. You know, the project is so big and has so many little bits. I don't see that we might already be doing it. It's a great question.
Yeah. Well, thanks. Let's thanks the speaker again.
Thank you.